Listen closely, because the examiner is literally waiting for you to drop easy marks right now. Seriously. In every single Cambridge Physics 0625 paper, there is a trap hidden right in plain sight: units and vector directions. You might understand the physics perfectly, but if you don't know exactly what the mark scheme is secretly demanding, your grade boundary is at immediate risk. Let's fix that.
So why does ordinary revision completely fail so many students when it comes to combining vectors? Well, it's because they walk right into the examiner's trap. They see a 3 and a 4, and they just write 7. By completely ignoring the direction, they just hemorrhage every single available mark. The examiner knows you're rushing, right? They're counting on you to treat a vector like it's just some basic scalar. Don't fall for it. And this is exactly why these strict rules exist in the first place. Just take a look at the flight deck of a passenger jet. These instruments provide absolutely crucial, life-saving information. Out there in the real world, confusing a scalar for a vector, or, say, misreading a physical quantity, that isn't just a dropped exam grade. It is a literal catastrophe. The examiner just wants proof that you respect these quantities exactly like a pilot would. Now, before any measurement can be trusted, we have to choose our standard, right? In physics, it's like building a house. We build everything on 3 foundational pillars: length, mass, and time. Literally every other unit scales up or down from these 3 within the decimal SI metric system. So if you fail to anchor your calculations to these basic SI quantities, I promise you, your final answers are going to immediately crumble. Okay, so how do we actually guarantee full marks? Well, we filter every single question through this 4-step high mark framework. Step 1, identify the core physics concept. Step 2, extract the precise evidence or data. Step 3, apply your scientific reasoning. And step 4, this is where like 90% of students mess up, lock it in with the exact examiner wording. If you align with these 4 steps, you're handing the examiner exactly what they want on a silver platter. Moving to step 2 of our framework, it requires pristine data handling. And that's exactly where the powers of 10 shorthand comes into play. Look, when you're dealing with massive numbers or super tiny measurements, writing out endless zeros is it's a massive risk for calculator errors. Instead, by simply moving the decimal, you can efficiently write 4,000 as 4 times 10 to the power of 3. Or a tiny measurement like 0.004, that's 4 times 10 to the power of -3. Mastering this little trick completely protects your method marks by stopping those incredibly frustrating miscounts.
Now, in just a moment, I'm going to reveal the exact, specific phrasing the examiner looks for to award full marks on incredibly small measurements. It is a massive clue that changes your answer completely. But hold on, before we unlock those top band marks, you absolutely have to master the core definitions that act as the whole foundation for these measurements. Listen, these definitions are non-negotiable. A scalar quantity has magnitude only. Think basic stuff, like mass or time. A vector, however, carries a magnitude and a specific direction, things like force or velocity. Think about it. If a question asks for a vector and you only write down the size, well, you haven't actually answered the question. You have to explicitly state the direction to even survive the concept step.
Right, so there's this whole red pen checklist of unforced errors that will just drain your method marks in practical questions. Missing units entirely, that's the absolute worst offense. But rounding your numbers way too early in a calculation, that's going to cascade into a wildly inaccurate final answer. Combine that early rounding with vague terminology or drawing conclusions that totally ignore your actual data, and your score is immediately capped. The crazy part? These traps are 100% preventable.
Okay, here is that exact phrasing I promised you earlier. You see, any single lab measurement is always going to carry some error. Always. So when the examiner asks how to accurately measure a tiny distance or a super short time interval, the exact wording they demand is measure multiples and take the average value. It's that simple. Time 10 swings of a pendulum, then divide by 10. Or measure the thickness of 100 pages and divide by 100. This specific technique scientifically crushes the size of your error. It's a total game changer. Let's actually put this into practice. I want you to pause for a second and evaluate this flawed car analogy. Imagine the question asks, a car travels 500 meters north in 10 seconds. State its velocity. Based on the framework we just covered, predict exactly why the answer, the speed is 50, scores so poorly. Like, what vital elements are just entirely missing here? All right, here's the examiner-style correction. That first answer, it was a total disaster. It used the wrong scalar term, it lacked a unit, and it completely ignored direction. The improved top-band answer correctly identifies velocity, it includes the SI unit meters per second, and, crucially, this is the big one, It locks in the direction, due north. Boom. That is exactly how you flawlessly execute what the examiner is expecting. Which brings us to a very rigid syllabus requirement. You have to be able to calculate or graphically determine the resultant of two perpendicular vectors. When you're combining them, you can't just mash their sizes together like a simple addition problem. No way. You have to account for their differing directions. You do this either by drawing an accurate scale model with a protractor or calculating it using geometry. That final direction arrow, it is just as critical as its length, for sure.
0. Yep, that is exactly how many marks your calculation will get if you fall into the trap of early rounding, or if you write down substituted values without their proper units. Even if your final number magically matches the mark scheme, if the examiner cannot see clear step-by-step substitution using the correct SI units, they are literally instructed to give you 0 method marks. You have to prove the physics, not just the math. It's harsh, but it's true. So, to absolutely bulletproof your grade, just run through this exam-safe checklist. Number 1, have you chosen the correct simple apparatus? Number 2, is your method clearly stated? Number 3, are your substituted values written with their actual SI units? And number 4, if it's a vector, is the direction explicitly written down? If you lock these 4 things in, your marks are totally secure. Okay, so you now know how to secure marks for basic measurements and vector directions. Awesome. But how do you survive when the examiner suddenly twists these exact concepts into a massive practical data graph trap? Think about it. What happens when these measurement concepts are suddenly tested through deliberate anomalies, super tricky graph scales, and really demanding gradient calculations? The traps get much deeper from here. To bridge this gap and make absolutely sure you secure those vital top band practical marks, we need to decode the exact anomalies and graph traps the examiner uses to filter out the top students. You've got the measurement foundation down. Now it's time to apply it to the absolute hardest question types. In the incredibly precise world of physics, a number without a unit or a direction isn't data. It's just a meaningless scribble. Are you ready to turn those scribbles into undeniable proof? Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click the next explainer on your screen right now, and I'll see you over there to uncover the final examiner trap.